This building has never installed a single air conditioner since the day it opened, yet it sits in a country where outdoor temperatures swing from 5 Fahrenheit at dawn to 95 Fahrenheit by afternoon, and its interior has held a stable 73 Fahrenheit year-round for nearly 3 decades. It's called the Eastgate Centre, and it was engineered by copying the internal structure of an insect mound, cutting energy consumption by 90% compared to a conventional building of the same size, using no compressors, no refrigerants, and no mechanical cooling of any kind. But if this design is really that effective, why isn't every office tower on Earth built this way? And what exactly did engineers copy from an insect to pull this off? Let's find out. The idea of regulating a structure's internal climate without burning fuel or consuming power is one of the oldest engineering solutions in nature. We've already covered variations of this mechanism. Persian wind catchers used to do this by funneling desert breezes down into lower levels while pulling hot, stale air out through the top. But long before any human architects solved this problem, termites had already perfected it. In the savannas of southern Africa, macroterms termites build mounds that can rise over 9 feet tall, engineering structures that maintain an internal nursery temperature within 1 degree of 87 Fahrenheit, regardless of whether the outside air is freezing at night or scorching at noon. These weren't simple piles of dirt. They were precision climate machines, refined over millions of years of evolutionary trial and error. Biologists studying these mounds in the 1960s and 70s began to suspect that the internal tunnel networks weren't random, but a deliberately engineered ventilation system. By the 1990s, this theory had matured into something an architect could actually use. The breakthrough came in 1991 when a Zimbabwean architect named Mick Pearce was commissioned to design a mixed-use office and retail complex in Harare. Pearce's original brief called for a building that could stay comfortable through Zimbabwe's brutal temperature swings without relying on imported, expensive, and power-hungry air conditioning systems that the national grid could barely support. And unlike anything built in the region before, his design had no compressors, no refrigerant lines, and no mechanical cooling plant of any kind. Pearce's creation was simple, yet extremely clever, drawing on the same 3 principles termites had already solved. During a typical Harare afternoon, solar radiation heats the exterior masonry and turns a conventional building's upper floors into a thermal reservoir. Temperatures inside sealed offices can climb rapidly, and that heat doesn't just sit there. It forces air conditioning systems to run longer, work harder, and consume more electricity just to maintain a livable temperature. And in most commercial towers, the ductwork carrying cooled air runs directly through those superheated spaces, meaning the air is warming back up before it even reaches the desks it's supposed to cool. So the entire point of Pearce's design was to break this cycle, move the hot air out before it ever has a chance to build up. And that is exactly what the termite-inspired structure was designed to do, using 3 principles working together. The first is thermal mass. The building's walls are built from dense, exposed concrete and brick, materials that absorb heat slowly during the day and release it slowly at night, smoothing out the extreme daily temperature swings before they ever reach the interior. The second is the stack effect. Vertical chimneys built into the structure allow warm air to rise naturally and exhaust through the roof, drawing cooler outside air in through low-level vents, mimicking the exact chimney network termites carve into their mounds. The third is a system of 48 brick chimneys and 32 fans, low-power fans, not compressors, that circulate air through hollow floor spaces, pulling cool night air in and storing it inside the exposed concrete slabs to be released slowly throughout the following day. The key point here is that unlike a sealed office tower which just relies on brute force refrigeration to fight the outside temperature, the Eastgate Centre uses the building's own mass and the movement of air to do most of the work. And the more extreme the daily temperature swing, the harder the system works in its own favor. But here's what most people don't realize. The system doesn't stop regulating temperature when the fans are off. You see, it also leverages the enormous thermal inertia of the concrete itself, which continues radiating stored coolness for hours, creating a gentle temperature buffer that persists long after the sun goes down. And this simple design has been proven to be remarkably effective. Independent monitoring of the Eastgate Centre found that it uses approximately 10% of the energy that a conventional air-conditioned building of the same size would require, while maintaining occupant comfort levels comparable to fully mechanically cooled offices nearby. And developer records show that the passive design saved roughly $3.5 million in upfront air conditioning infrastructure costs alone, savings that were reinvested directly into the building's construction budget. To put that in practical terms, a conventional HVAC system of that scale would have required a chiller plant consuming hundreds of kilowatts continuously. Eastgate's fans draw a fraction of that, and because the thermal mass does most of the passive regulation, every dollar of energy savings compounds year after year. But these numbers come with an important caveat, and it's part of the reason why buildings like this remain rare outside of a handful of showcase projects. A study of biomimetic ventilation systems found that while thermal mass strategies work exceptionally well in climates with large daily temperature swings, they perform far less effectively in humid tropical regions where nighttime temperatures never drop low enough to recharge the concrete's stored coolness. Their conclusion was that this approach is powerful, but only within a specific climate band, and outside that band, the passive system alone isn't enough. And this is where proper climate matching becomes critical. Architects generally recommend a daily temperature swing of at least 20 Fahrenheit between night and day for the strategy to work efficiently. In consistently humid, low-swing climates, additional mechanical backup becomes necessary. But the climate limitations are only one piece of the story. The most problematic barrier has been construction complexity. The defining feature of this design, exposed heavy masonry paired with a precisely calculated network of chimneys and vents, is also its primary point of difficulty. Getting the airflow calculations wrong at the design stage can leave a building stuffy in some zones and overcooled in others, producing complaints that a standard mechanical system simply doesn't generate. Cheaply designed imitations are especially prone to this, which over the years has given passive-cooled buildings a reputation as risky and unpredictable compared to conventional HVAC. And there's a more subtle engineering problem called thermal lag mismatch. This occurs when the concrete mass is sized incorrectly for the building's actual occupancy pattern, so the stored coolness releases at the wrong time of day, arriving hours after it's actually needed. For this reason, most engineering firms recommend detailed climate modeling before committing to a fully passive system, a step that adds cost and time most developers aren't willing to spend. But beyond the engineering, there is the issue of familiarity. Passive thermal mass buildings look and behave differently from conventional towers, and in commercial real estate, predictability drives leasing value. Standard glass and steel towers, by comparison, are a known quantity that banks, insurers, and tenants understand immediately. Developers across the world have frequently avoided biomimetic designs because they disrupt the standardized, replicable formula that makes financing and leasing straightforward. And even in regions with ideal climate conditions for this approach, many developers work around the uncertainty by defaulting to conventional mechanical systems anyway, even when a passive approach would perform better, simply because it's the path everyone already understands. Building codes have also made it more difficult to implement passive thermal design at scale. As commercial construction has become standardized around guaranteed, measurable mechanical performance, codes in many countries now require certified HVAC capacity, regardless of a building's passive design features. Because a thermal mass system's performance depends on climate variables no engineer can fully control on paper, it falls into a regulatory gray area. So the real question we should be asking now is whether more buildings should be designed this way. And the honest answer depends entirely on where you're building and what you're trying to accomplish. If you're in a region with large daily temperature swings, the high plateaus of southern Africa, parts of the American Southwest, or similar semi-arid climates, a termite-inspired passive design remains one of the most cost-effective ways to slash your cooling load. The upfront cost of exposed thermal mass construction runs comparable to conventional masonry building, while the fan and chimney infrastructure adds a modest fraction to that budget. For a mid-sized commercial building, the energy savings can offset that additional design cost within the first several years of operation. And because the approach eliminates most mechanical cooling infrastructure, it also removes the ongoing maintenance and refrigerant costs that come with a conventional chiller plant. But in consistently humid climates or in buildings with unpredictable high-density occupancy patterns, a fully passive system is probably not a suitable standalone choice. In these conditions, the daily temperature swing needed to recharge the thermal mass simply doesn't exist, and a hybrid approach becomes necessary instead. In reality, for most developers today, particularly those building in variable or humid regions, a hybrid system, thermal mass paired with a smaller supplemental mechanical backup, is probably the more practical choice. A well-designed hybrid can still cut energy consumption by 50% or more compared to a fully conventional building, while avoiding the risk of a fully passive system underperforming during an unusual weather event. There are fewer unknowns, fewer tenant complaints, and no reliance on a single climate pattern holding steady year after year. If you liked this video and enjoy learning how nature has already solved the engineering problems we're still struggling with, then subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. And if you want to see how a completely different species solved the problem of pulling drinking water directly out of thin air in the driest desert on Earth, then you need to watch our video on fog harvesting nets right here.